Okay, can you see the slide?
Yeah.
Okay, good. So yeah, that's the name of the talk, and let's see if I can get this to work. All right, so the story that I'm going to talk about today starts with an infinite product, and it's probably an infinite product that almost all of you know, namely that 1 plus x to the 2 to the I, which can be written out as 1 plus x times 1 plus x squared times 1 plus x to the fourth, and so forth, that if you then work this out, what you get is that this is just 1 over 1 minus x. And why is this? It's just because every positive integer has a unique representation as a sum of distinct powers of 2. So for example, if you want the coefficient of x to the fifth here, well, you write 5 in base 2, and then you pick the 1 that corresponds to 2 to the 0. You don't pick the 2, but you pick the 1 corresponding to 2 squared, and you get 4 plus 1 is 5. And because every integer has a unique representation, and every power occurs exactly once, and you get 1 over 1 minus x. Okay, so now you might say, well, what if we play with this a little bit? What if we change the plus signs to minus signs? So then what happens? Well, then we get the same sort of product. And what does it look like? Well, it now has both plus and minus signs in it. And maybe you can see right away what this is going to be. This is going to be the 2A Morse sequence, which we already heard mentioned previously in this day of short talks. So here it occurs as minus 1 to the Tn, where Tn is the parity of the number of ones in the base 2 representation of n. Okay, so here we see that, of course, because it's minus 1 to the Tn, all the coefficients of this power series are either 1 or minus 1. And before they were all 1, right? So now they're all 1 and minus 1. Okay, well, then we might try another variation. We might say, okay, let's change the powers of 2 to Fibonacci numbers. Why not? So then the numeration that I'm going to pick for Fibonacci numbers is f0 is 0, f1 is 1, and fn is the sum of the 2 preceding. I think that's the standard way to represent them. So let's multiply out this infinite product. And what does it look like? Well, here are the first few coefficients. And you can see that unlike before, where we had plus or minus 1 coefficients, now there are some 0 coefficients, right? The coefficient of x cubed is 0, coefficient of x to the 6th is 0, and so forth, right? So you might say, well, then what are these coefficients? So let's write it as a of n, x to the n. And then the question is, what is a of n? So in particular, just from this little experiment that we just did, we can see that the coefficients seem to be either 1, 0, or minus 1. And so that might be something you would want to experiment with. And you can type this into Maple and produce a few hundred or a few thousand coefficients and check to see that they're all 1, 0, or minus 1. So is that true? And I guess another question is not simply, is it true, but is it obviously true? Well, first of all, to see that there's something non-trivial going on, if I replace the Fibonacci numbers with, let's say, what's sometimes called the Tribonacci numbers, where every number is the sum of the 3 previous instead of the 2 previous, then the coefficients of the corresponding power series turn out to be unbounded. So there actually is something slightly unusual going on. So this was first proven, and the fact that a of n is either minus 1, 0, or 1, this was first proven by Neville Robbins in 1996. And his proof is, I would say, elementary, but not so easy, and is largely case-based. And here's just a picture of part of the proof. So here he's using this a as the coefficients again, and you see he has some rather complicated case structure, depending on parities of various things, and this is just part of the proof. Well, then later on, Federico Ardila in 2004 found, I think, a much nicer proof, a simpler proof of this fact. But his proof still requires some kinds of complications and an induction. And again, here's part of the proof. So he's splitting up an interval into 3 subintervals, and he argues that in a particular interval, we get the numbers that are similar to another interval, but perturbed by -1, and so forth. You know, I like his proof very much. And when I read his paper, I thought, oh, that's a much nicer way of doing it. But I have to say that neither of those really suggested how to prove a generalization if there were one. And so at the time when I read it, I thought, oh, maybe there would be some other way to do this. So here's a sketch of another way to handle this. So what we'll do is we will first obtain an expression for A of n in terms of Fibonacci representations of integers. Then we'll create a deterministic finite automaton, or DFA, that's based on a construction of Berstel, that what it does is it normalizes non-canonical Fibonacci representations. In other words, you start with an illegal Fibonacci representation and it turns it into a legal one. And that's what the transducer did. What the DFA does is it takes an illegal Fibonacci representation in parallel with a legal one and checks to see if they evaluate to the same thing. And from this, we can find a linear representation for A of n, so an expression in terms of matrices, and then we just show that the space of possible values of this linear representation is finite, and in fact, is just -1, 0, and 1. And the point is that a lot of this is just purely computational. That is, it doesn't require any thought at all. You can just use existing software, type it in, and get the result. And lately, I've been really interested in results that don't require any thought. Maybe it's because as I get older, I get stupider, and I prefer to have the computer do the work for me. But I really like proofs where you don't have to think at all. Okay, so now Robbins already noticed back in his original paper the connection between the coefficients A of n and the total number of representations of n as a sum of distinct Fibonacci numbers, and he called this R of n. So for each n we can say, okay, how many different ways can we get n as the sum of distinct Fibonacci numbers where order it doesn't matter. Okay, and so you could also let Re of n be the number of representations of n as the sum of an even number of distinct Fibonacci numbers, and Ro of n denote the number of representations of n as the sum of an odd number. And then clearly, R of n is just going to be Re of n plus Ro of n, right? That doesn't require much thought. Now, every representation of n as the sum of an even number of distinct Fibonacci numbers in our infinite product, well, because there's a minus sign there, if we get an even number of distinct Fibonacci numbers, then this is going to multiply -1 by itself an even number of times. So that's going to contribute 1 to our quantity A of n that we're trying to study, this coefficient in this power series. And if n is a sum of an odd number of distinct Fibonacci numbers, we'll get an odd number of -1s multiplied together. So that'll contribute a -1. So A of n is just Re of n minus Ro of n. And now we just combine it with what we previously saw, and we get A of n is 2 Re of n minus R of n. So to compute A of n, we just have to compute these two things: the number of representations of n as a sum of distinct Fibonacci numbers, and the number of representations of n as a sum of an even number of distinct Fibonacci numbers. Okay, well, so let me just remind you what Fibonacci representation is very briefly. It is a way of writing n as EI-FI, where these coefficients are 0 and 1, and where we never have two consecutive ones. So for example, 23 is 21 plus 2, F8 plus F3, and we don't have two consecutive Fibonacci numbers there. And this is the canonical Fibonacci representation, sometimes called the Zeckendorf representation. And then if we have a string of zeros and ones, we could let W with a subscript F to be the number denoted by summing the appropriate Fibonacci numbers together, starting with the most significant digit. And we could define round parenthesis F to be the canonical Fibonacci representation. Okay, so what did Berstel do? In his 2001 paper, he created this 4-state transducer that can convert any Fibonacci representation to its canonical one. And what we'll do is we'll just rewrite his transducer. It's exactly the same machine, but it's just written as a DFA. And it takes 2 Fibonacci representations in parallel and accepts if the second is the normalized version of the first. So here it is. That's Berstel's machine, just rewritten as a DFA. So for example, 23 can be represented both by this in Fibonacci representation and by this. This is the normalized version. And if we feed in this string of pairs of digits, so 0, 1, then to 1, 0, then to 0, 0, then to 1, 0, then to 1, 0 again, then 1, 1, and then 0, 0, we see that we get to an accepting state. And so indeed, the normalized version of this representation is this one. Okay, so now that we have Berstel's automaton, we can find a formula for R of n, which is the number of representations of n as the sum of Fibonacci numbers. Namely, if y is the canonical Fibonacci representation of n, then R of n is just the number of strings x, such that x is the same length of y, and x evaluates to the same integer as y, or the number of strings x, such that our machine A accepts the pair xy. So this pair is meaning that we write x and y in parallel and evaluate it. So this means that it's the number of length y paths, length of y paths in A, whose second component is labeled with this canonical representation y. But that is just a linear representation, which we can read off directly from the automaton. This is the transition function on 0. This is the transition function on 1. This is the initial states. These are the final states. And so this gives us a formula for R of n as a matrix product corresponding to this matrix valued morphism mu applied to n written in its Fibonacci representation. Okay, now we've done R of n. Now we have to do Re of n, the number of Fibonacci representations for n having an even number of parts. So to do this, we just take Berstel's automaton and we just say, okay, our x must have an even number of ones in it. So this is just a cross product where we're counting ones. It multiplies the number of states by 2. Now we have 8 states. Now we get 8 by 8 matrices. We get another linear representation for Re of n. And this can be done purely mechanically by a system like Grail, for example, that lets you form cross products of automata, or any kind of system that lets you manipulate automata. Okay, well, now we have 2 linear representations for Rn and Re of n. We can get a representation for A of n because A of n is twice Re of n minus R of n. What we do is we just say, all right, we'll make a linear representation with matrices of size 12, and we'll compute R of n, we'll compute Re of n in the first 8 by 8 upper left block, and we'll compute R of n in the lower 4 by 4 block, and we get this picture here. So, or maybe I said it wrong. Maybe I switched left and right. Anyway, we get this representation for A of n, which I didn't write down. And now it turns out that there's a very nice book, which everybody should have in their library, by Berstel and Ruthenauer, entitled The Non-Commutative Rational Series with Applications. And in there, you can find an algorithm that I think was originally due to Schutzenberger that tells you how to minimize a linear representation. And this is programmed up in Maple by a student of mine a long time ago. And I just ran it through there. And here we get the minimized representation. And now we have a formula for A of n. So again, all of this can be done just using existing software. And so you don't have to think about this at all. Okay, so now we can complete the proof of the Robbins-Ardila theorem. We just use breadth-first search to explore the space of vectors of the form y gamma of x, such that x is in 0, 1 star, and it turns out that this space is finite. It's of size 15, and furthermore, Sz is in -1, 0, 1. That completes the proof. So there we have a proof of the Robbins-Ardila theorem without doing very much work at all. Okay, well, it gives us something more now. Because that space is finite, that means that we can turn this into a finite automaton. So there's an automaton that on input, the canonical Fibonacci representation of n, written as a binary string, will compute a of n. So another way to say this is that this sequence of coefficients is Fibonacci automatic. And here is the automaton. So if we want, let's say, the coefficient of 4, we write 4 in Fibonacci representation, which is 1, 0, 1, and we get to the state labeled 5 with output 1, so the coefficient is 1. Okay, well, we can prove many other things too. So if you look in the Robbins and Ardila paper, they proved many other things about these coefficients A of n, and also R of n and Re of n. So for example, let's just take one theorem from the Ardila paper. He proved that almost all integers n satisfy A of n equals 0. And here by almost all, I mean all but a set of density 0. Again, this can be proved really easily now that we have this automaton, because almost all n have an occurrence of this factor in their Fibonacci representation. That's more or less the same idea that if you pick a random binary decimal, then it will have any fixed block of digits occurring with the expected frequency. Well, here, because this is a legitimate block in Fibonacci representation with no 2 consecutive 1s, then this will occur with the expected frequency in some sense, and so it'll occur infinitely often. But you can see that if you start in any state in this automaton and you read this block, you end up in state 3, which has output 0. And once it gets to state 3, it can never leave. So this is actually a synchronizing word for the automaton. And that shows that almost all n satisfy A of n is 0. And if you wanted more, if you wanted to know what is the asymptotic density of the n for which A of n is 0, you can obtain that too, right? But the point is that you can prove many of these things that were proved before, again, with very little work. Okay, so now the same kind of thing that I just said can be used to prove the following. And these are new results that weren't in the older papers. For example, instead of the number of even and odd Fibonacci representations, that is where the number of parts was congruent to 0 or 1 mod 2, you could define RMT of n to be the number of Fibonacci representations whose number of parts is congruent to T mod m. And then you could look at 3 instead. And it turns out that if you look at R3I of n minus R3I plus 1 of n, then this again is either -1, 0, or 1. So this is a generalization of the result to modulo 3, whereas before we had it modulo 2. Now, I have to say that there's some very nice papers by Felix Weinstein that have appeared in the literature and also on the archive, where he proves other interesting things. And when I showed this to him, he suggested checking the following thing, namely that R30 minus R31 times R30 minus R32 times R31 minus R32 is 0. That is, at least one of these pairs is always equal for all n. And we can prove this by the same method. And furthermore, we can prove that if we now go to modulo 4, then it's no longer the case that, that these coefficients are bounded. And this can also be proved by the same method. Okay, so that's basically what I wanted to say. So I have to say that it was a lucky chance that the last talk went over a bit because my talk was shorter than the prescribed time. But I don't think anybody really objects if a talk is slightly shorter. So I feel no shame. If you're interested in pursuing any of these any of the things that I talked about, here are the references to all the papers. And I should mention also the papers of Felix Weinstein, which you can easily find on the archive. So that's it. Thanks for listening.
Does anyone have any questions for Jeff?
I have one.
Yeah, go ahead, Jean-Paul.
That's of course a stupid question as usual. What kind of integers, of sequence of integers, do we know that have the same property when you take the infinite product with those exponents, give your A sub n belonging to finite set? So in base 2 you had those minus plus 1, and in Fibonacci you had minus 1, 0, 1. Is there any chance that other sequences of integers do have the same property?
Yeah, I did find a few others. If you try the Luca numbers, for example, starting at a certain point, not starting with L0, but starting with, I think, L1, it also has the same property and can be proved similarly. I also tried to compute, for example, the lexicographically least sequence for which the coefficients were either minus 1, 0, or 1, and it seems completely mysterious. So I have no characterization in general.
Thank you.
Any other questions?
Yes, Jeffrey. I wanted to ask you, but you are already answered. What about the Lucas numbers? So you already answered. And
yeah, it works if you start with L1 equals 1. Yeah.
My other question was, your infinite product, you started it at I equals 2 and not I equals 1. So you avoid the square at the beginning. So is this, I was just surprised. I would just an explanation of this.
You mean, why don't I have 1 minus x times 1 minus x?
Yes, you start.
Purely because that's what everybody else did.
Yes, but what happens if you start? Of course, you cannot start at 0 because it would be a vanishing product, but you started one step further.
Yes, I don't know off the top of my head, but it's something we could easily do.
Okay.
Any other questions?
I have maybe a quick question. In that problem, each of the terms is y minus x to the power of a Fibonacci number. And what about 1 plus x to the power of a Fibonacci number?
Yes, that's R of n. If you do 1 plus x, that's R of n, the number of representations of.
Right.
Yeah.
Yeah, thanks.
Anything else? All right. Well, thanks again.